Okay, Chemistry 1411, continuing on with our ACS-like final exam review. We left off somewhere around question 47 in our last lecture. We have a galvanic cell here set up. It says, which statement is true regarding the galvanic cell in which an electric current is being produced? I'm going to give you a second to take a look at this and see if you can come up with an answer. Just going to get organized here quickly. All right. So now that you've had a chance to take a look at this, we normally write the galvanic cell such that the anode is on the left-hand side. So we have our anode over here. Then we have our cathode over here. And I told you to remember anox and red cat, right? The anode is where oxidation occurs. And reduction is where the cathode occurs. So if we take a look at these possible answers, remembering that a galvanic cell is a spontaneous reaction, right? This is a cell that's just going to cause a flow of electrons to occur spontaneously. So we say in A, we see that it says oxidation occurs at the copper electrode. Well, if this is a spontaneous reaction, we know that E cell for our reaction is equal to the standard cell potential of the cathode, subtract the standard cell potential of the anode. Okay, so we have E cathode minus E anode, so we would have 0.34 volts, subtract negative 0.76 volts, which of course gives us a spontaneous reaction 1.10 volts. So that looks good, okay? We have our copper as being our cathode, and we have the zinc as being our anode. Well, oxidation is not occurring at the copper electrode because the copper electrode is the cathode, right? And that is where reduction is going to occur. So we'll cross this out and we'll put reduction here. Next, it says B, the mass of the copper electrode is increasing. Well, if we have our flow of electrons going from the anode where oxidation is occurring, right, the electrons are flowing in this direction, what happens is that the electrons are coming down into here where we have the copper 2+ ions, and when they combine with the electrons, we're forming solid copper, right? So copper is depositing on the copper rod, and so the mass of the copper electrode is increasing. In C, it says zinc ions are being produced at the copper electrode. Well, there's no zinc ions over on the cathode side, so that's incorrect. Copper ions are being produced at the copper electrode. No, copper ions are being reduced, right? So copper ions are being reduced. So how could I phrase it? They're being eliminated, or they're being consumed at the copper electrode. And so the correct answer is B. As the electrons flow from the anode to the cathode, the copper ions are being reduced and solid copper are depositing onto the copper rod. All right, number 48. It says, given the standard reduction potential of cadmium and nickel, so these are just the standard reduction potentials that you would find in a table of standard reduction potentials. It says, which pair is going to react spontaneously? Is it nickel plus and solid cadmium? Is it the cadmium plus and the solid nickel? Which one is it going to be? Like, how are we going to put these together? Well, you know that in order for the cell to react spontaneously, that the E cell has to be a positive number, right? If our E cell is positive, then our delta G is negative. And we also know from the last question that the standard cell potential is going to be equal to the standard reduction potential of the cathode plus the standard reduction potential of the anode. Well, how would I combine these two numbers, negative 0.25 and negative 0.4? Did I put plus when I meant subtract? Nobody corrected me. Did I do it correctly up here? Yeah, okay. Had a lapse of judgment. I think I saw a positive here, just threw in a positive there. So it's supposed to be E cathode minus E anode. Anyhow, I was like, that doesn't work when I took a look at the numbers. Anyhow, how would we take negative 0.25 and negative 0.4 and plug them into this equation here and end up with a positive number? Well, the only way that I do that is if I choose the more negative reduction potential. So that for cadmium, if I choose that as my anode. So the anode is always going to be the most negative. So if I plug these numbers in, I get that the E naught cell is going to be equal to negative 0.25 volts subtract negative 0.40 volts, and that gives me a positive cell potential, which is 0.15 volts. And so that means that I want to have nickel as my cathode. This is going to be my cathode. And a cathode, that's where reduction occurs. So I need to have a nickel 2+ ion. Can cancel these ones out. And the oxidation is going to occur at the anode. Now I have to reverse this equation. So I need to have solid cadmium, which is going to be oxidized to produce cadmium ions. And so the answer is B. It's a reaction between nickel ions, which get reduced, and cadmium, which gets oxidized to cadmium 2+. Number 49 is a question that I would expect my students to get pretty quickly. In a spontaneous reaction, the anode is always going to be the most negative. Yes, if it's spontaneous, okay, if the reaction is spontaneous, anode will always be most negative, right? If you're subtracting a negative and you want it to be positive, the larger negative is going to have to be the anode in order to make a positive number. Question 49 says, which statement best describes a dynamic chemical equilibrium? One where the reverse reaction rate is 0, one where the forward reaction rate is 0, the forward and reverse reaction rates are 0, and when the forward and reverse reaction rates are equal. Who could tell me which one would be the best answer here? In a chemical equilibrium, yeah, absolutely. It's when the rate of the forward and the reverse reaction are identical, right? That's the whole point behind equilibrium. That's why we use equilibrium arrows like that, because the forward reaction rate and the reverse reaction rate are identical. Question number 50. We have this system in equilibrium. We have 2 sulfur dioxide plus oxygen produces 2 moles of sulfur trioxide. We disturb the equilibrium. The equilibrium is disturbed by increasing the amount of oxygen. When the equilibrium is reestablished, the new concentrations of SO2 and SO3 are increased and decreased and decreased and increased and all kinds of stuff. Well, if we increase the amount of oxygen, what's that going to do? That's going to push the equilibrium to the right side, right? If we're increasing the amount of oxygen, it's going to push the equilibrium to the right. What's that going to do? That's going to cause an increase in the amount of sulfur trioxide, and it's going to reduce the amount of sulfur dioxide. So decrease and increase. Which one is that? B. All right, just some equilibrium, and we looked at many examples of equilibria. We, in fact, dealt with 3 chapters where we covered equilibria. The equilibrium chapter and the acid-base equilibria, the equilibria of other reaction classes. So 3 full chapters where we dealt with equilibria. Question number 51, more equilibria, right? It says, which factors will affect both the position and the value of the equilibrium constant for this reaction? Increasing, so we want to affect both the position of the equilibrium, yes, and the value of the equilibrium constant. So, son of a gun, I didn't need to do that. What happened here? And we also want to affect K. So the K and the position of the equilibrium is what we'll call it. If we increase the volume of the container, right, it's going to push the equilibrium to this side, right? Because we have 4 moles of gas on this side and we only have 2 moles of gas over here. So yeah, increasing the volume of the container definitely is going to affect the equilibrium, but it's not going to change the equilibrium constant, is it? If I remove some ammonia gas, that's going to push the equilibrium to the left-hand side, right, to reestablish the concentration of ammonia. So it is going to affect the equilibrium, but that's not going to change K. In B, adding more nitrogen gas, it has the opposite effect of C. You're going to push the reaction to the right-hand side, which will affect the equilibrium, but it's not going to affect K, is it? But if I lower the temperature, since this reaction is exothermic, right, that's going to push the reaction to the right-hand side, right, because heat is a product. So if I'm removing heat, it's going to push the reaction to the right. So it will affect the equilibrium, but we know that a change in temperature is the only thing that's going to affect K. That's going to affect our equilibrium constant. Give me a thumbs up if you got that one right. You noticed right away that changing the temperature is going to have an effect on the equilibrium constant. We went over that many times over the course of the semester. Oh, good. Okay, great. Thanks, Mackenzie. Good. A smile and a thumbs up. All right, let's move on. Question 52. More equilibria. It says the equilibrium constant, Kp, for this reaction. We have 2 sulfur dioxide plus oxygen gives you 2 sulfur trioxide. Seems like somebody's obsessed with this reaction. Our Kp is 0.5 at 750 Kelvin. What is the equilibrium constant Kp for this reaction at the same temperature? All they did is manipulate the first equation, didn't they? They took this reaction and they manipulated it. Now, how did they manipulate it? You see that they reversed it? What happens when you reverse? Well, when you reverse the reaction, that's the same thing as taking 1 over the Kp. What else? Does anybody see what else they did besides reverse the reaction? What other thing did they do? They reversed it and they did something else. Yeah, thanks, Ashton. Absolutely. Ashton, Amanda, Joey, you're all 100% correct. All right, they also halved it or divided it by 2. So we'll say, what did my student say? He said halved it. So halved. So that's going to be the same as taking the Kp and putting it to the power of a half like that. So if you put those together, what do you get? You get 1 over Kp to the power of a half, or 1 over the square root of Kp. So if the Kp is 0.5, let me grab my calculator. I take the square root of 0.5, and then I take the reciprocal, and I get 1.4. So is that an answer? Yep. So the answer is 1.4. So you have to know how to manipulate a K based off of what is done to a reaction. And so I went over that in class. I think I had 1 slide, I know, where I summarized all the rules, maybe even 2 slides. I don't remember. But anyhow, it's 1.4. There we go. I'm going to erase that because I need space to solve this one. So question 53, a solution contains 0.0010 molar lead-2 nitrate, same concentration of manganese 2 nitrate, and the same concentration of zinc nitrate. Solid sodium hydroxide is added until the hydroxide concentration is 3 times 10 to the negative 6 molar. Which statement is true? Okay, well, this one is a question that we would have looked at in, which chapter was it? The equilibrium of other classes. So this is a chapter 15 type problem. So if you want to go back and look at chapter 15, where we compared QSP to KSP, right? And then we said if QSP is greater than KSP, we get precipitation. If it's lower than KSP, we don't get precipitation. Now, what I noticed right away is that for all 3 of these, whether you have lead-2 nitrate, manganese 2 nitrate, or zinc 2 nitrate, they all produce the same concentration of lead, manganese, and zinc, don't they? Right? So if either one of these dissociates, like I'll just show you one, for example, you have lead-2 nitrate, right? And you have 0.0010 molar. Well, when it dissociates, you end up with 1 lead-2 plus ion and 2 nitrates. We don't give a crap about the nitrates, pardon my language, but you end up with 0.0010 molar for the lead 2. You end up with double for this. It's 0.0020, but that's neither here nor there, because when we go to calculate our QSP of lead 2 hydroxide, manganese 2 hydroxide, and zinc hydroxide, the KSP, let me write it out like this. The QSP for lead 2 hydroxide, so lead 2 hydroxide dissociates to give you lead, not palladium, I got palladium on the brain here, I guess, plus 2 hydroxides, like that. We know the concentration of the lead is 0.0010 molar. We know the concentration of the hydroxide. It's 3.0 times 10 to the -6. And I have twice that concentration. So if I take, I'm just taking my calculator here. If I take 3 times 10 to the -6, multiply it by 2, then I square it. No. Sorry, my QSP, son of a gun. I hate solving these on these things. My QSP is equal to the concentration of my lead 2 plus times the concentration of my hydroxide squared. Now let's try it. So I have my QSP for all 3 of these is going to be the same, right? Because the concentration of the cation is the same in all of them. Let's write it out. 0.0010 multiplied by, what was it? 3.0 times 10 to the -6 squared. So let's try it again. 3 times 10 to the -6 squared multiplied by 0.001. Okay, so the QSP for all 3 of these is identical. It's 9.0 times 10 to the -15. Okay? Give me a thumbs up if you follow me on that the QSP for all 3 of these solutions is identical, right? The concentration of the cation in each one of these is 0.0010, and the concentration of the hydroxide, it even tells you in the problem, it's the same for all of them. So they all have the same QSP. Does everybody follow me on that? Cha? No? Does anybody follow me on that? If not, okay. All right. If you don't, stop me. I really don't like solving problems in these little tiny sheets, but anyhow. So if they all have the same QSP, well, you see that for the lead hydroxide, that the QSP is greater than the KSP. And therefore, the lead is going to cause, or it's going to form a precipitate. All right, that's going to form a precipitate. You see that the QSP is less than the KSP for the manganese hydroxide. And so that is going to have no precipitate formed. And then for the zinc hydroxide, you see that the QSP is greater than the KSP. And so it's going to form a precipitate. Therefore, which ones are going to precipitate? The lead hydroxide or the lead 2 hydroxide, and the zinc is going to precipitate. So both of these will precipitate. And again, I'm just reviewing here the reason why the manganese 2 hydroxide is not going to precipitate, son of a gun, is because its KSP is higher than my QSP. So I haven't reached a high enough concentration of the cation and the anion in order to cause precipitation. All right. This is why you need scratch paper when you're doing a chemistry exam, right? Question 54. For this chemical reaction at 25 degrees Celsius, the concentration of the product is blank, the concentration of the reactants at equilibrium. So you have this reaction here, C2H4 gas plus H2 gas is in equilibrium with C2H6 gas. My Kc is 1.3 times 10 to the 21. You see that your Kc is much greater than 1, isn't it? It's huge. You have a huge Kc. If my Kc is huge, which side will the reaction lie to? Will it lie to the side of the products, or will it lie to the side of the reactants if my Kc is really, really big? I mean, it's 10 to the power of 21. I'm going to have mostly reactants or mostly products. Yeah, it's going to be mostly products. And so the concentration of products will be greater than the concentration of the reactants. It's by far, you know, there'd be very little reactants with an equilibrium constant that's that big, okay? So that's just what? A matter of you knowing when you see a giant equilibrium constant, it's going to be mostly products, nothing more than that. Okay, question number 55. You got a redox reaction in which three electrons are transferred. It's got a delta G of 18.55 kilojoules per mole. What is the value of the standard reduction potential? What is the value of E cell? Well, we know the formula that delta G is equal to negative N, which represents the number of electrons, multiplied by the Faraday constant, multiplied by E naught. So if we're solving for E naught, we can rearrange this formula to E naught is equal to delta G divided by N over F. Well, our Faraday constant F, I'll just write it over here, is 96,485 joules divided by volts. If you look at the handout that I'm going to give you, you even see that in the list of constants. We have the two values of R, then you have the first value for the Faraday constant, then it tells you 96,500 joules per volt, which is close enough to 96,485. Anyhow, there we go. So we've got our Faraday constant and we've got our delta G. We've also got the number of electrons, right? N is equal to 3. The only thing we have to do is change the delta G into joules, and we know that in 1 kilojoule, we have 1,000 joules. So when I plug in some numbers here, I get that my E naught is equal to 18.55 times 10 to the power of 3 joules per mole divided by N, which is 3 electrons per mole that are transferred in the reaction, multiplied by the Faraday constant. And again, you can use 96,485, you can use 96,500. Either way, you're going to get the right answer. Joules per volt. We see that joules cancel, as do moles. And we end up with the number of volts for each electron. And so we end up with a number that is, what is it? Negative 0.064 volts. So just a matter of using the formula and plugging in the numbers and being sure that you do the conversion of kilojoules into joules. And if you look at the handout that you have for the final exam, you'll see that this formula is in the list of formulas. Delta G is equal to negative NFE. You see the list of equations, and it is in there. All right, number 56. What is the pH of a buffer solution? Containing 0.11 molar sodium acetate and 0.09 molar acetic acid. They give you the Ka for acetic acid. Well, sodium acetate or acetate is the conjugate base of acetic acid, right? We've seen acetic acid come up Avogadro's number of times. Acetic acid, which is CH3COOH. Its conjugate base is CH3COO minus. So these are conjugates. Therefore, we can use the Henderson-Hasselbalch equation. It is on the list of equations. You see that it has pH is equal to the pKa plus the log of the concentration of the conjugate base divided by the concentration of the acid. So all we have to do is plug some numbers in. We get that our pH is equal to the pKa, which is the negative log of the Ka. We're given the Ka, so we have the negative log of 1.8 times 10 to the negative 5 plus the log of the concentration of the conjugate base, which is 0.11 molar divided by 0.090 molar. I'm going to leave molar out because it would cancel anyway. And we get 4.74 plus 0.09. And we get that the pH of our buffer solution is being 4.83. Here we go. Number 57, what is the pH of a 0.23 molar barium hydroxide solution? If we have a solution of barium hydroxide, when that dissociates, we get the barium cation, plus we get twice the amount of hydroxide ions. They told us that our initial concentration of our barium is 0.023 molar. We have none of these. Then that's going to dissociate completely. Barium hydroxide is a strong base. We're going to lose 0.023 molar. Here we're going to gain 0.023 molar. And here we're going to gain 2 times 0.023 molar. So equilibrium, we have none of this. We have 0.023 molar barium ions, and then we have 0.046 molar hydroxide. We're going to first start by calculating the pOH, which is equal to the negative log of the concentration of the hydroxide ion. That equals negative log of 0.046. We get that our pOH is equal to 1.34. Remember that pH plus pOH is equal to 14.00. So we can solve for our pH, which is equal to 14.00 minus the pOH. So we get 14.00 subtract 1.34, and we get that our pH is equal to 12.66. That's something that everybody should be able to do relatively quickly. I'm not a speed guy. I'm not really into timing myself when I, solve problems, but I would think that that's a problem that you would be able to answer relatively quickly. Okay, it shouldn't take you, 3-4 hours. It should take you, 3-4 minutes at the most. What's the approximate pKa of the weak acid titration? Of the weak acid in the titration curve, right? We have a strong base, sodium hydroxide. Okay, we have our weak acid, right? We're starting at a pH of around, around 3, and then we're adding base, we're adding base, we're adding base. We get to the equivalence point here, and then we've got more and more base, so we get to a really basic pH. Well, if I take a look at this, okay, and I draw a line down from the equivalence point, which is around here, right? This is the equivalence point. Well, halfway through that line is around here, okay? This would be the 1/2 equivalence point. And I know that when I titrate a weak acid with a strong base, that the pH is going to be equal to the pKa at the 1/2 equivalence point. So what's my pH at the 1/2 equivalence point? Well, my 1/2 equivalence point, again, is somewhere around here. So if I draw a line over like that, my pH is equal to 5. And so my pKa is going to be equal to around 5, right? And if I look at all the possible answers, the only one that's anywhere near 5 is B, which is 4.8. Last question deals with some nuclear chemistry. One of the recently named elements is element 117, tennessine. Identify the missing particle in the nuclear reaction that produces this element. Well, we know that the sum of all the mass numbers have to tally up in the reactants and the products to give us the same number. So we have I can barely even read that. What is that, 249? Yeah, 249 plus something gives us 293 plus 4, right? We have 4 neutrons, so 293 plus 4. What am I missing here? 293 plus 4. No, that looks reasonable. So I have 249 plus x, I'll call it, is equal to 297. So I get the x is equal to 297 minus 249. I get the x is equal to 48. So I have 48 as my mass number. Oh, look, there's only one with a mass number of 48. It's kind of a goofy question. Could have made it a little tougher. But anyhow, let's keep going. I see that the atomic numbers have to tally up. So I have what? I got 97 plus x plus something is equal to 117. So x is equal to 20. So we have 20. You go over to the periodic table. You look up element number 20. What is it? Calcium. And there you go. Calcium 40.